In this lesson, you're finally going to be introduced to instantaneous rates of change. We've done tons of work with average rates of change, and you know how to calculate those. But how do we calculate an instantaneous rate of change? That may seem like an impossible task to figure out how something is changing in an instant. But let me intro you to a few different ways we're going to be able to figure out what the instantaneous rate of change is. So have a look over here at this green nonlinear function that I've just highlighted. Now that function clearly does not have a constant rate of change over its domain. But I could find the average rate of change between any 2 points on that function, right? Theoretically, we have the equation of that green function, so we could find the coordinates of any 2 points on that function. And I could find the average rate of change between those 2 points just by finding the slope of the secant line that connects them. And finding slopes of secant lines is no problem for us, right? If we have 2 points on a line, we can find its slope just by doing change in y over change in x. Okay, so we can find the average rate of change between 2 points, but how do we find the instantaneous rate of change at a single point? Well, remember the rate of change formula is change in y over change in x, but at a single point, there is no change in y and there is no change in x. This is undefined. 0 divided by 0 is undefined. So how do we figure out the rate of change at a single point? In this lesson, you're going to figure out that the instantaneous rate of change at a point can be represented by the slope of a tangent line that touches the function at that single point. So if we could figure out the slope of that tangent line, we would know the instantaneous rate of change. But how do we find the slope of the tangent line? Just because we know that's what represents the instantaneous rate of change, that still leaves us with a problem. How do we find the slope of that tangent line? We only know a single point on the tangent line. The only point we know is the point that touches the original function that we have the equation of. We don't know the coordinates of any of these other points. So before you actually learn calculus and the Newton's quotient, it's important to understand the different estimation techniques we could use to come up with the slope of that tangent line. So in this lesson, I'm going to go over a few of those estimation techniques with you. So there are lots of different ways that we could estimate the slope of a tangent line. In this lesson, I'm going to take you through a few of those ways. Graphically, we could find the slope of a secant line on a surrounding interval, or we could average the slope of a secant line from a preceding interval and a following interval. Or we could actually just guess a point on the tangent line and then guess the slope of that tangent line. Algebraically, there's actually a little bit more of an accurate way of doing this. We could find the limit of what the secant slopes are approaching as the change in the x values approaches 0. And we'll talk about that, and you'll get introduced to the idea of a limit. So when you're ready to learn about all of these different estimation techniques for finding the slope of a tangent line, head on over to jensenmath.ca to get a copy of the lesson. And we are in the Advanced Functions course, and we are in Unit 6, and we are on the 3rd lesson, Instantaneous Rates of Change. Once you're on this page, you can get a blank copy of the lesson that you can fill out as we go through the video lesson here. And after the lesson is over, you can get your practice problems here. And as always, you can check your solutions after you try the practice problems by clicking on Worksheet Solutions. So let's get started. Okay, let's get started with the lesson. So let's fill in the first couple blanks here. I already talked about in the introduction what a secant line and tangent line tell us, right? An average rate of change corresponds to the slope of a secant line that connects 2 points on a function. So for this green function, I would know the coordinates of all the points on it. The average rate of change between this point and this point could be represented with the slope of that secant line, and we could definitely calculate that just using a slope formula. An instantaneous rate of change, on the other hand, is represented by the slope of a tangent at a single point. So if we wanted the instantaneous rate of change at a single point on the green function, we would need to know the slope of the tangent line that touches the function at that single point. But like I mentioned to you in the intro, it's going to be difficult to find the slope of a line where we only know 1 point on it. So I'll take you through a few estimation techniques we could use to estimate the slope of that tangent line. But before we calculate some instantaneous rates of change, let me make sure you remember how to calculate average rates of change. It turns out that average rates of change are going to be key to us being able to calculate instantaneous rates of change. So in this example, it gives us a function, h at t equals this quadratic function, where the height is in meters and t is in seconds, and it's about the height of a ball. and it says determine the average rate of change of the height of the ball for each time interval. So these are time intervals. These are not points, they're time intervals. This means from a time of 0 to a time of 0.5. We need to figure out what's the average rate of change of the height over that time interval. And then same thing here, what's the average rate of change of the height over this time interval? So for both of these questions, we're looking to find the average rate of change. I'll represent that with m, which would be equal to the change in height over change in time. And let me just make sure you understand what we're finding graphically. So let me head over to Desmos. Okay, so here's that quadratic function. The y values are the height, the x values are the time, and we're looking for the average rate of change, first of all, between the interval when time is 0 to when time is 0.5. So that could be represented with this secant slope. Here's the height when time is 0, it's at a height of 1, and here's the height when time is 0.5. The height is at about 6.775. And we could calculate those y values, right? We could calculate those y values just by plugging those x values into this function here, and that's what Desmos is doing for us. So we know the coordinates of those points. We could find the average rate of change of the height by finding the slope of that secant line. And when you have 2 points on a line, find the slope of it is easy. Just change in y over change in x, or like in this question, change in h over change in t. So let me just add in an intermediate step. I'm doing the height when time is 0.5 minus the height when time is 0. When I did it in that order, what I did was the y coordinate here minus the y coordinate here. So I'm making this like my second point, and this is my first point. So when I do the difference in the time values, I have to make sure I follow that same order. So I have to do the second time value, 0.5, minus the first time value of 0. And then we had Desmos calculate for us what h at 0.5 and h at 0 were. But if you needed to calculate on your own, you would just plug them into this formula, and it would tell you the height. And then we can evaluate this, and we get the slope is 11.55. And we should write the units. We were doing our change in height divided by change in time. Our height was in meters, our time was in seconds, so we did meters divided by seconds. So the average rate of change is 11.55 meters per second. That means over this interval, if I zoom in on here, we can see that it's not a constant rate of change, right? The red part is the actual function. It's slightly curved, but we know the average rate of change between those 2 points, represented by the slope of that secant line, is 11.55 meters every second. It looks like it's going up by almost 6 full meters in half a second, so that our answer makes sense of going up by 11.55 meters in a full second. Let's now do the next interval. So we want to know the average rate of change of the height with respect to time between a time of 1 and 2.5 seconds. So we're now finding the average rate of change between this point and this point. The average rate of change between 1 second and 2.5 seconds. Well, the height is going up for a little bit, and then it starts going down, but on average, what's the rate of change of height with respect to time over that interval? We can find that average rate of change by finding the slope of the secant line between those 2 points. So I just have to do the change in the heights divided by the change in the times, and that will tell me the average rate of change between those 2 points. So I'll make this one my second point and this one my first point, and then I'll find my change in height over change in time. So I decided to make my time of 2.5 my second point, so I will do h at 2.5 minus h at 1. These are just my heights. I need to divide that by the change in time. So my second time value minus my first time value. Right, when you do slope, you always do y2 minus y1 over x2 minus x1. So that's why I keep saying second and first values, just because I know you're familiar with that type of formula. And then we can calculate h at 2.5 and h at 1 by plugging them into this formula, but we have Desmos calculating them for us. It was 5.375 minus 10.1. And this is all over 1.5. And then we'll get the average rate of change between the 2 points by evaluating that fraction. And we get negative 3.15 meters per second. So that tells us on average, the ball is falling by 3.15 meters per second over that interval. The ball was going up at the first part of the interval, but then it was going down after, but on average, it's going down by 3.15 meters per second over that interval. Alright, let's actually calculate some instantaneous rates of change. So in this section, we're transitioning from average rates of change to instantaneous rates of change. And remember, an instantaneous rate of change is the exact rate of change of a function at one specific value of the independent variable, and we can estimate it using average rates of change for small intervals of the independent variable. So this point about small intervals is going to be very important. We don't know how to calculate slopes of tangent lines, but we do know how to calculate slopes of secant lines. So if we can calculate slopes of secant lines over very, very small intervals, it'll give us a good representation of the slope of the tangent line. And we'll talk a lot more about that, and specifically about this last part that says the best estimate for the instantaneous rate of change occurs when the interval used to calculate the average rate of change is made as small as possible. Making it 0 is a bit of an issue. We've already established that, because then we would have 0 over 0 for our rate of change. But we want to make it as small as possible. So at the end of this lesson, when we calculate the limit of secant slopes, we're going to talk a lot about that. So let's move on to an example where we actually estimate an instantaneous rate of change. So we're working with this same height function. It's the height of the ball with respect to time. Here's the graph of that function right here. Example 2 says, find the instantaneous rate of change of the height of the ball at 2 seconds. So at 2 seconds, where is the ball? At 2 seconds, the ball's height is right here. I could calculate the height, the y value of this function, or in this case the h value, by plugging 2 into the equation. And if I plugged 2 into this equation, I would get 9.4. So we could calculate this 9.4 value by plugging in 2 for time in that equation. So I know the height of the ball at 2 seconds, but I need to know how is the height changing with respect to time at that single point. Well, you might say, well, it's not changing at all, but remember, we could represent the rate of change of the height of the ball at that one exact point with the slope of a tangent line that touches the function at that one exact point. So how do we find the slope of this tangent line that touches the function at that one point? Well, actually, I don't know if this tangent line that I drew is perfect, but how are we going to find the slope of it? Well, we can do kind of what I just did. Method 1 is to actually just draw a tangent line. Do your best to draw a tangent line, so a line that touches the function over some interval at just one single point. And then try and guess the slope of it. And by guess the slope of it, I mean, well, to find the slope of a line, we need 2 points. And we only know one point on this line. It's the point it shares with the red function, the height function that we know. So we just have to try and find another point on this line and guess the coordinates of it. This point right here, it looks like it's pretty close to being a lattice point. It looks like it's at pretty close to 3.5 comma 2, maybe 3.5, 1.95, I don't know, but I'll guess 3.5 comma 2. This may not be an exact point, but I've guessed, because the tangent line I drew may not be perfectly accurate. But this is a guess, this is an estimation of another point on that tangent line. So if I want the slope of the tangent line, I know one point on the tangent line for sure, and another point that may be close to being on the tangent line. Let's find the slope of the line connecting those 2 points, and then that's a good estimate for the instantaneous rate of change of the height function at that single point. So since we're estimating an instantaneous rate of change, let's use the notation for instantaneous rate of change. It would be dh over dt, the difference in height over the difference in time, but when written like this, we know it means the instantaneous rate of change of height with respect to time. And then I'm going to draw this vertical line, and then write t equals 2. The reader would know that this means the instantaneous rate of change of height with respect to time when time is 2. And I'm going to write an approximately equal symbol because this is an estimate. We're going to estimate it by doing change in y over change in x for these 2 points, for this point and this point. I'll just do y2 minus y1 over x2 minus x1. So I'll choose this to be my second point, doesn't really matter, and do 2 minus 9.4, that's my change in y values, divided by my change in my x values, 3.5 minus 2. And this is my estimate for my instantaneous rate of change, negative 7.4 over 1.5. and I got about negative 4.93. And this is in meters per second. So what we just figured out is, at this point, we think the ball is falling at a rate of 4.93 meters per second at this one single point. That's our guess. There are other ways to estimate the slope of this tangent line. The second method would be to actually calculate a slope of a secant line over a surrounding interval. So what we do is we choose an interval that has the instantaneous rate of change location as its midpoint, if possible. And as I mentioned earlier, we want to make the interval as small as possible. So if I want the instantaneous rate of change of the function at 2, I could pick an interval that surrounds it. So let's say when x is 1 to when x is 2.5, and I could get the coordinates of those 2 points, and then I could find the average rate of change between those 2 points by finding the slope of the secant line that connects them. There's only one problem. That secant slope doesn't look like a great representation of that tangent slope. And I had Desmos draw in that tangent line for us, just so we could see what it looks like and have a good reference point. When we're actually doing this question, we don't actually have that tangent line drawn for us, but it's a good reference point to know what we're aiming for. So that secant slope, I mean, it's not far off from that tangent slope, but it's not great. We could do better by making the interval smaller. So how about between 1.5 and 2.5, like the question asks? So that interval is smaller, and the smaller the interval, the better. In fact, it would be even better if I did between, let's say, 1.9 and 2.1. If I found the secant line that connects those 2 points, that would be really close to matching that tangent slope. But the question says use the interval between 1.5 and 2.5, so that's what we'll do. So we'll find the average rate of change of the function between those 2 points. Notice the interval between these 2 points surrounds the x value of 2. The x value of 1.5 is before, the x value of 2.5 is after. And now what we can do is we can find the average rate of change between those 2 points. And notice that secant slope, I mean, it's not the exact same slope as the tangent line, but it's pretty close. It should give us a good estimate for what the tangent slope is. And we can get the coordinates of these 2 points just by plugging the x values of 1.5 and 2.5 into our equation, and we can get the y values that go with those 2 x values. Okay, getting Desmos to calculate those y values for us, I got 10.975 and 5.375. So I can get a good estimation for the slope of that tangent line, so the instantaneous rate of change when time is 2, by calculating the slope of that secant line. So the slope of the secant line I can calculate just by doing my change in height over my change in time. I have the coordinates of both of the points on that secant line, so I can calculate the slope of the line connecting them. Since we're estimating instantaneous rate of change, I'll use the notation for instantaneous rate of change, dh over dt. That means the instantaneous rate of change of height with respect to time, when time is 2, is approximately equal to my change in my heights. So 5.375 minus 10.975. So I did that height minus that height. So make sure when you find your change in times, you follow that same order and do that time minus that time. So 2.5 minus 1.5. And our calculation would give us negative 5.6 meters per second. So we know over the interval from 1.5 to 2.5, on average it's falling by 5.6 meters per second. So we'll use that as our guess for how the height is changing at the point in the middle of that interval, the point when time is 2. So our guess for the slope of the tangent is negative 5.6. A third method is to average the slope of a secant line in a preceding and following interval from the point. So what we could do if we wanted to estimate the slope of that tangent line, I could find the slope on an interval before a time of 2, and the slope on an interval after a time of 2, and then average those 2 slopes. So if I want the slope of this tangent line, notice before a time of 2, secant slope is less steep than the tangent line, so it's not falling quite as fast over that interval. And after a time of 2, the secant line is steeper than the tangent line, so it's falling faster. So what's happening at that point? Probably about the average of those 2 secant slopes. So that's another method for estimating the slope of the tangent. Find that slope, and then average them. and that should give us a decent estimate for the slope of that tangent line, which is an estimate for the instantaneous rate of change of height at a time of 2. So once again, I'll have Desmos calculate the y values for us. So notice these are the same points we actually used in the previous example. This is just about a bit of a different way of thinking about estimating the slope of the tangent. This point here was 1.5, 10.975, and this point here was 2.5, 5.375. So we know the coordinates of all three of the points we're going to need to calculate these two secant slopes. So let's find the secant slope over the interval between times of 1.5 and 2 first. And I'll find the slope of the secant line connecting those 2 points. So I'll find the average rate of change between those 2 points. So the slope would be equal to the change in height over the change in time. And I'll consider that my second point and that my first point. So I would do 9.4 minus 10.975 divided by the change in my times, so 2 minus 1.5. And I get an average rate of change between those 2 points of negative 3.15 meters per second. How about over the next interval, so from 2 to 2.5? If I found the slope of that secant line, I would do change in heights, so 5.375 minus 9.4. divided by the change in times, 2.5 minus 2, and I'll get the average rate of change between those 2 points, and I get negative 8.05 meters per second. So I know the rate of change on the interval preceding the time of 2 is negative 3.5 meters per second, and the average rate of change on the interval following a time of 2 is negative 8.05 meters per second. So it's falling slower before, faster after. So what do we think is happening at that point? We could say that the average of those two slopes would be a good estimate for the slope of that tangent line. So our estimate for the instantaneous rate of change of the height with respect to time, when time is 2, would be approximately equal to the average of those two secant slopes. How do we average two numbers? We just add them and divide by 2. So negative 3.15 plus negative 8.05 divided by 2. And we get negative 5.6 meters per second. Notice that's the same answer we got doing method 2, the surrounding interval, and that will always happen if the points you're using are evenly spaced around the point you're doing the instantaneous rate of change at, right? We're 0.5 less than a time of 2, and then 0.5 greater than a time of 2, so the two methods are going to result in the same answer. So really quick summary. In example 2, we did 3 methods for estimating the slope of the tangent line. Method 1 was draw the tangent line, calculate the one point we know it shares with the function we have the equation of, and then estimate another point, find the slope of that line using those 2 points, and that's an estimate for the slope of the tangent line. Method 2, find the slope of a secant line on a surrounding interval. So pick 2 points that surround the single point that we want the instantaneous rate of change at, and calculate the secant slope connecting those 2 points. Or calculate the slope of a secant line on an interval before the point that we want the instantaneous rate of change at, and then calculate the slope of a secant line on an interval following the point that we want the instantaneous rate of change at, and then average those two secant slopes, and that's a good estimate for the instantaneous rate of change. In example 3, we're going to estimate some instantaneous rates of change when we don't actually have the equation of the function, and we also don't have the graph. All we have is a table of values that tells us information about a few points. So consider the data from the Bank of Canada for the beginning of November in 2007. Estimate the instantaneous rate of change of the value of the Canadian dollar on November 7th. So on November 7th, the value of the Canadian dollar is 91.7 US cents. So 100 cents Canadian is worth 91.7 cents American on November 7th in 2007. We have information about a few days in November before November 7th and a few days in November after November 7th. If we want to estimate the instantaneous rate of change of the dollar on that day, there's a couple methods we could use. We could either use the method of calculating an average rate of change on a surrounding interval, so the average rate of change between those 2 points, or we could do method 2, average a preceding and a following interval. So we could find the average rate of change on an interval prior to November 7th and calculate the average rate of change on an interval after November 7th and then average those two. And notice when I was doing these two methods, I was keeping the intervals as small as possible. That's what gives us the best estimate. An interval from 1 to 14, yes, does surround November 7th, but that's not as small as possible. The smallest interval possible that surrounds November 7th would be the interval between those 2 points, between November 5th and November 8th, based on the information we're given. So let's do these two methods. The first method says use a surrounding interval. So I will find the average rate of change on the interval from day 5 to day 8. So I will use that point and find the average rate of change between those 2 days. And I want the average rate of change of the value of the dollar with respect to the day. So my estimate for the instantaneous rate of change of the value with respect to the day, that's the unit of time, so I'll call it t, when time equals 7 is approximately equal to, I would have to do my change in my values divided by the change in the days. I'll make this my first point and this my second point. So when I do my change in value over change in time, I'll do the value on day 8 minus the value on day 5 divided by 8 minus 5. So this would be equal to 93.06 minus 93.39 divided by 8 minus 5, which is 3. And that's equal to negative 0.11, and we are in cents per day, right? The value is in cents, and the time is in days. So cents per day is the rate of change we found. So we found out the value of the Canadian dollar is going down by about 0.11 US cents per day over that interval between November 5th and November 8th. So that's our estimate for the rate of change on November 7th. How about if we do the second method? We'll average the interval before November 7th and an interval after November 7th. So we'll start by finding the average rate of change between these 2 points, between this point and this point. So I'll do the value on day 7 minus the value on day 5 over 7 minus 5. And the value on day 7 was 91.7 US cents, minus the value on day 5 was 93.39 US cents. All this divided by 7 minus 5, so divided by 2. And I get negative 0.845 cents per day. So on the interval before November 7th, it's dropping by about 0.845 cents a day. Let's see what's happening after November 7th. So on the interval from November 7th to November 8th. So from November 7th to November 8th, let's find the average rate of change between those 2 points. So the average rate of change would equal the change in the values. So I'll do the value on November 8th minus the value on November 7th divided by the change in time, so 8 minus 7. And the value on day 8 was 93.06, and the value on day 7 was 91.7, and this is all over 1. And I get an average rate of change of 1.36 cents per day. So on that interval, the value of the Canadian dollar is actually going up by about 1.36 US cents per day. So on the interval before November 7th, the value is going down. On the interval after, the value is going up. So what do we think is happening on November 7th? A good estimate would be the average of those two things. So an estimate for the instantaneous rate of change of the value with respect to time on November 7th would be approximately equal to the average of those two numbers. So we just add them and divide by 2. And we get about 0.2575 cents per day. So that's our estimate for the instantaneous rate of change of the value of the dollar on November 7th. We think it's going up by about 0.2575 US cents per day. Notice this one is a different answer than we got using method 1, and this time they're different because the intervals that we used are not evenly spaced. The interval between day 5 and 7, those are 2 days apart, and between day 7 and day 8, that's only 1 day apart. So when those intervals are not evenly spaced, these two methods can give you different answers. One of them tells you the value of the dollar is decreasing on November 7th. The other one tells you the value of the Canadian dollar is increasing on November 7th. So two different answers. Neither of them are exactly correct. These are just estimates. Okay, the last part of this lesson, and this is the most important part because this is going to lead us into limits and then into calculus. So this is going to be an important example to understand. We're going to find an instantaneous rate of change just from the equation, no graph. So what we're going to do to introduce you to limits is we are going to squeeze a preceding or following interval to estimate an instantaneous rate of change. What do I mean by squeeze? We're going to find average rates of change that get progressively smaller, right? The smaller the interval is, the better the estimate it is for the instantaneous rate of change, the slope of the tangent. It then says you can make more accurate estimates as to what the rate of change is approaching at an exact point. So instead of just calculating one secant slope and using that as the estimation, we're going to look at a pattern of what secant slopes are approaching as the interval gets smaller and smaller and smaller. So let me show you what I mean. We're going to be working with this function here, 2x cubed minus x. And we're going to try and calculate the instantaneous rate of change at an x value of 2. So we want the slope of that tangent. Now I have Desmos graphing that tangent for us, and I have it telling me the slope of that tangent is 23. So I know the slope of that tangent is 23 just because Desmos told me. But how can we use secant slopes to figure that out? Well, we know any point we want on this function. We know all of the x and y coordinates because we have the equation. So what we're going to do is we're going to use a following interval, so an interval after an x value of 2, and we're going to calculate a slope of a secant. This secant slope, so the interval from 2 to 3.5, that secant slope is 45.5. So that's not even close to the tangent slope of 23. And you can see graphically that green slope does not come close to matching that blue slope. But if I move this point closer, so if I make the interval smaller, so if I move it to when an x value is at 3, I can find the slope of that secant line. The slope of that secant line is 37. That's a closer match to the slope of the tangent. And as I move the point even closer, notice the slope of the green line starts to get closer and closer to the slope of the tangent line. So you might say, well, okay, well, let's just move those 2 points right on top of each other. Well, what happens then? If we try and calculate the slope of the secant line, we get undefined. If the change in the x values is 0, then we get 0 divided by 0 for our secant slope calculation, and that's nonsense, that's undefined. So what we have to do is look at the trend and what's happening to these secant slopes as we move the points closer and closer together, so as we make the intervals smaller and smaller together. We look at what are these secant slope values trending towards. What are they approaching is the terminology we will use. Notice it looks like they're approaching 23. So let's actually do this algebraically, and we're going to do it in a nice table. So use the chart below to estimate the slope of the tangent to the curve f at x equals 2x cubed minus x at x equals 2. So I just have picked 1, 2, 3, 4, 5 intervals for you to do, and notice each of the intervals gets smaller and smaller and smaller. This interval has a change in x of 1, this has a change in x of 0.5, then of 0.1, then of 0.01, then of 0.001. So the intervals are getting smaller and smaller. So the slopes of the secants will get to be better approximations of the slope of the tangent. But what we're going to do is analyze the pattern and what are those secant slopes approaching. And that will give us the best estimate we've gotten yet for the slope of a tangent line. So I've filled out the first row for you. I'm just showing you, so all we're doing is we're finding the slope of a secant line connecting an x value of 2 to an x value of 3 on the function. So we're finding the slope of that secant line, that green line, an x value of 2 to an x value of 3. So we have to calculate those y values, 51 and 14, by plugging 3 and 2 into this equation. So I've broken up the calculation of change in y over change in x into parts. Do the change in y here. So we'll do f at 3 minus f at 2, and you'll see we get 51 minus 14. We get the 51 and 14 by plugging the 3 and the 2 into this actual equation. But we had Desmos do that for us. We got 51 and 14. So our change in y value is 37. Change in x values, we'll just do 3 minus 2. The change in x values is 1. And then in this last column, we actually do the change in the y divided by the change in the x, and we get the slope of the secant line. Let me do one more while explaining it to you. and then I'll just fill in the rest quickly for you. So how about the secant slope connecting 2 to 2.5? So that would be this green secant slope connecting those. So I would have to do f at 2.5, I would need the y value for when x is 2.5, minus f at 2. This will give me my change in my y values. And if I plug this one into the equation, I saw Desmos gave me 28.75, and f at 2, well, we calculated that already, that is 14. So the change in y is 14.75. My change in x, do 2.5 minus 2, and I get 0.5. So now I need to do change in y over change in x. So I'll do 14.75 divided by 0.5, and I get 29.5. Okay, hopefully you see how this works now. So we've gotten two secant slopes. Let's keep making the intervals smaller and smaller and see what those secant slopes are approaching. So just fill it out with me as we go along here. Okay, now that all the calculations are done, let's just look carefully at all of the slopes of the secants we found. So we found the slope of the secant over the first interval. When the interval width was 1, the secant slope was 37. And then as we decreased the width of that interval, the secant slope went down to 29.5, to 24.22, to 23.1202, down to 23.012 when the points were only 0.001 units apart. And notice I kept a ton of decimal places as I was doing this. Keep all of the decimal places. That's very important when you do these types of problems so that you can really see the trend in what the secant slopes are approaching. So what we just found is something called a limit. By looking at the limit of the secant slopes, as we approach an x value of 2, we can estimate the slope of the tangent to be, well, what do we think these values are trending towards? From 37 to 29.5 to 24 to 23.12 to 23.012, it looks like it's approaching 23. So we can estimate the instantaneous rate of change of y with respect to x at an x value of 2 is 23. So just to remind you what we did, we found what these secant slopes, I have calculated here, are approaching as I move this point infinitely close to the point when x is 2. So I looked as I moved the point closer and closer and closer, what was happening to these secant slopes. So they went from 37 closer and closer and closer and closer to a secant slope of 23 as I moved the points infinitely close together. So as the change in x approached 0, the secant slopes were approaching 23. And that's what we wrote here. So that's it. Next, what we're going to do is the big part of what you're going to need to do as you enter calculus is you're going to need to know about limits and Newton's quotient. So that's what's coming up next. So that's it for this.